All right, this is lab 2 for physics 2211, looking at motion of a falling object. Whoa, okay. The purpose of this lab was to observe the motion of an object that is being dropped from rest and falls somewhat slowly straight down, and I personally used a clementine. The models that were used here was a video analysis software called Tracker that allowed me to track the object's position over time accurately, as well as a computational simulation using GlowScript and Python. The principles that were simulated here was the second law of motion, as well as the momentum principle, as well as acceleration due to gravity and drag. In the results here, there was a discrepancy between the observed model and the computational model that was factoring in only the force of gravity, and the computational model that was factoring in both the forces of gravity and drag was much more accurate. All right, so here you could see the clementine being dropped and falling in a straight line. The system here was the clementine, and the surroundings included the hand that dropped the clementine from rest, as well as the floor and the earth, constantly acting on all objects. So here, as the observed motion points, as well as the graphs. So you can see here, I created these graphs by pinpointing the clementine's position at different timestamps throughout its motion, and the observed start time was 0 seconds here. The initial position was this, and the initial velocity was calculated using the first 2 data points in our table, as well as the time of the last observation was 0.585 seconds. And you can see here the clementine's motion in the y direction was decreasing and speeding up as time went on. So here was this computational model created using the initial velocity and the initial position got taken from the observed motion in Tracker, and then assuming all other forces were constant. So here we input the clementine's estimated mass, as well as the gravity, magnitude of acceleration due to gravity, and the velocity update formulas and the position update formulas. So the velocity update formula implemented the Newton's second law of motion due to assuming acceleration is equal to the force divided by the clementine's mass. And then here we also calculated the net force by only including the force of the weight, which was the clementine's mass times gravity times j hat. And we only incorporated the force of gravity here, as you can see, and the velocity versus time here was velocity was decreasing at a constant rate, so constant acceleration here. And we can also see that the position in the y direction was a little bit bigger than what we had in the observed motion, which was negative 1.29, and here was negative 1.77. Okay, let's look at incorporating the force of drag now. So here, this was much more accurate, negative 1.27 compared to the negative 1.29, because we incorporated the force of drag, which is basically a resistance force opposing motion of a object moving through a fluid, typically increasing with speed. And it plays an essential role of air resistance in dynamics of falling objects. So here we can see that the acceleration was decreasing as time went on. So here, this is the Newton's second law of motion, or the momentum principle. Here, the acceleration of an object depends on 2 variables: the net force acting on the object and the mass of the object. And again, drag is a force whose direction is always the opposite of direction of the object's motion, and the magnitude of the drag in this experiment was proportional to the square of the object's speed. And due to that, we could see that in our second computational model where we incorporated drag, we could much more easily determine the terminal, find the terminal velocity because of the force of drag pointing up, made it exactly balanced with the force of gravity after a period of time, which means that the net force at some point was equal to 0. And due to this Newton's second law of motion, the acceleration also became 0. And the object will start falling at a constant speed after a period of time, which basically means it has reached its terminal velocity of its motion. So that is why our second computational model incorporating the drag force allowed us to see the terminal velocity of the clementine. Again, the discrepancies here was a graph of the observed motion was identical to the computational model when we did not incorporate the force of drag. Even when we did incorporate the force of drag, it was still kind of a little bit different. even though the computational models were built on the observed data. So what could be the sources of error? So first, the simplification in our model, even incorporating the force of drag, sometimes because we assumed that the magnitude of the drag was proportional to the square of the object's speed, it might not have been that in real life. It might not be that exact proportionality of square of the speed. And again, plotting errors on my part when I was plotting the location of the clementine at different timestamps, that could also vary based on my accuracy with that. And what if the object was initially thrown downward? Would terminal velocity be the same or different? So if the object was thrown downward, the terminal velocity, it would have been moving with a higher velocity, and the acceleration would have made it move faster. So it would have taken the force of drag a longer time to kind of balance out and have the net force equal 0. So it would have reached the ground faster as well. And in conclusion, we analyzed the motion of a slowly falling object by capturing video data and developing computational models to consider both gravity and drag forces. In the future, this experiment can be improved on refining different measurement techniques and exploring additional variables to improve accuracy. But overall, we saw that drag had a significant effect of air resistance and dynamics of falling objects.